foreground avoidance.
Good afternoon, everyone. My name is Srijita. I'm from IIT Kharagpur, and today I'm going to present our work on 21 centimeter intensity mapping using the Tapered Gridded Estimator, which is a power spectrum estimator that we have developed to measure the 21 centimeter multi-frequency angular power spectrum and from it the power spectrum of the 21 centimeter signal from the high redshift universe. Uh, now, since a lot has already been talked about the importance of detecting the 21 centimeter signal, let me start from the part where what we are trying to do is we are trying to make a statistical detection of the 21 centimeter signal through power spectrum estimation using radio interferometric observations. So this is the system that we are considering, where there are the telescopes over here which are pointing towards this direction in the sky and observing this volume. And this frequency basically substitutes for the line of sight distance information. Now, the brightness temperature fluctuations within this volume can be decomposed in terms of spherical harmonics like this. Then the multi-frequency angular power spectrum for the 21 centimeter for the brightness temperature fluctuations at two different frequencies can be defined by the correlation of these ALM coefficients at two different frequencies and by taking an ensemble average over different statistically independent realizations. And these fluctuations can also be decomposed in terms of the Fourier, in terms of a Fourier series, and the correlation between different K modes gives us the power spectrum of the brightness temperature fluctuations. Now, under the flat sky approximation, which is the case for small field of view of observations, the multi-frequency angular power spectrum as a function of frequency separation, where delta nu is basically the magnitude of the difference between nu A and nu B, are related to the power spectrum by a Fourier transform along this delta nu direction. Now, we start with the visibility data, which is the fundamental quantity that is measured in any radio interferometric observation, which is defined as the Fourier transform of the specific intensity distribution in the sky, modulated by the primary beam of the telescope. And each visibility measurement will have an additive system noise, which we assume to be a Gaussian random variable with zero mean and some RMS 2 sigma n square. And we assume that the noise in two different visibility measurements are uncorrelated for two measurements at two different baselines, two different frequency separations, and for different timestamps of observations. Now, as has been discussed before, the visibilities are mainly dominated by these foreground components, which are around 10 to the power 4 to 10 to the power 5 times higher than the signal, 21 centimeter signal that we are trying to detect. And the various strategies that have been developed to deal with these foregrounds generally falls into these two categories: foreground removal and foreground avoidance. So foreground avoidance is what we have considered for this work. And what happens is that the foregrounds are generally spectrally smooth. So along this K parallel axis, which is proportional to the Fourier conjugate of this frequency axis, because of the spectral smoothness, the foreground is expected to be confined within this finite wedge-like region, which is known as the foreground wedge. And ideally, we would expect to expect these K modes to be free of foregrounds where we can detect the 21 centimeter signal. Now, to describe our estimator, we start with the visibility measurements at the baseline uy and some frequency nu a. Which in terms of the Fourier transform of the specific brightness temperature fluctuations is given by this with this additive noise. Now, this is the UV plane, and each point in this UV plane has a measured value of the visibility. So what we do is we divide this UV plane in rectangular grids, and at each grid point, we calculate a convolved gridded visibility by convolving the visibilities with a window function like this. And this factor Fi basically takes care of the flagging in the data. So if there is a bad data, then that channel is, and if the channel is flagged, then this Fi has a value 0, so that it does not contribute to this gridded visibilities, and otherwise it has a value of 1. Now this W tilde function, convolving function, is chosen so as to taper the primary beam pattern at these higher angular distances, so that the foreground contributions, residual foreground contributions that are coming from outside of this outer part of the primary beam gets tapered and suppressed in the estimated multi-frequency angular power spectrum and power spectrum. So this is the expression for the GMRT primary beam pattern, and we see that this theta W square, which is defined as F theta naught, here theta naught is 0.6 times the full width half maxima, and F is the parameter which controls the tapering in the estimator. So as we decrease the value of F, we see that the side lobes are getting suppressed more and more. Now, having this convolved gridded visibilities, we then correlate the gridded visibilities in 2 different frequencies to get an estimate of the multi-frequency angular power spectrum. This term that has been subtracted is to subtract the noise bias. So we assume the visibilities in 2 different baselines, frequency channels, and timestamps are uncorrelated. So we subtract out the self terms to subtract the noise bias, so that we get an unbiased estimate of the multi-frequency angular power spectrum. And this mg factor is the normalization factor, which we calculate using simulations. So we considered unit multi-frequency angular power spectrum for which CL nu A nu B is equal to 1, for which this left-hand side becomes 1, and then we get the mg as this factor for the unit multi-frequency angular power spectrum. So what we do is we generate multiple realizations of this U maps, and we calculate, simulate the visibilities corresponding to that U maps, and then we apply our estimator identical to what we do in the actual data, visibility data, to calculate the value of this mg. And the ensemble average of this this estimator gives us an unbiased estimate of the multi-frequency angular power spectrum at a multipole Lg, where Lg is equal to basically 2 pi Ug, where Ug are these different grid points. Now, since the power spectrum is related to the multi-frequency angular power spectrum through a Fourier transform, so we can discretize this and write it in and invert it and write it in terms of matrix notation like this, where this noise, where this A matrix basically contains this Fourier coefficients, and this noise is then the additive noise in the measured values of CL delta nu. So then the maximum likelihood estimate of the power spectrum is given by this, where N is the noise covariance matrix. Now, from here we obtain the cylindrical power spectrum, which can then be further bent spherically to get the spherical power spectrum, spherical 1D power spectrum. Now what we have done is we have applied this estimator to an uGMRT data at a central frequency of 432 megahertz, which corresponds to a redshift of around 2.28, and we considered a subset of this entire observation, where we considered 1000 channels centered at this frequency, having channel separation like this, and we considered 25 hours of the observation, which were taken through over 4 nights. So we have considered individual nights and also the all nights combined. Now, for this particular sub-band, we see that the May 6 data has the least amount of flagging due to bad data, and the least amount of RMS sigma n. So the results that I am going to show is mainly for this May 6 data, and then we have also considered the data for the combined nights of observation. And here we use the flagged, calibrated, and point source subtracted data, where we apply the tapered gridded estimator, and this show the visibility, this show the UV distribution of the May 6 data and the combined nights data, and the baseline density of the May 6 data and combined nights data. And as expected, we see that the baseline density is greater for the combined nights data. So we have first validated our estimator with a simulation of where we considered this input model power spectrum with this spectral index n is equal to -2, and we generated multiple realizations corresponding to this input power spectrum, and we simulated the visibilities corresponding to those realizations, and then we applied our estimator to calculate the multi-frequency angular power spectrum and the spherical power spectrum from those simulated visibilities. So these show the mean values, these data points show the mean values that we obtained from the estimator, and the solid lines show the model, the analytical values of the CL delta nu, which is calculated using this equation, and along with 2 sigma error bars at 3 different values of L. So we see that the results match quite well within this 2 sigma error bar with the input model. And here we show the input model power spectrum along with the data points and the 2 sigma errors. Here we show the fractional deviation, and we see that apart from this point, the rest of the K values are within 5% fractional deviation away from the input model power spectrum. So we could recover the input model power spectrum quite well over the entire K range. So now these are the results for the multi-frequency angular power spectrum that we obtained. So this show the multi-frequency angular power spectrum at 2 different L values over the entire frequency separation and for 5 megahertz zoomed in. So what we see that these multi-frequency angular power spectrum are first of all foreground dominated, and the foreground signatures are shown by these oscillatory patterns that we are observing over here. So any point source at some distance theta away from the phase center is expected to contribute to the multi-frequency angular power spectrum by this cos term, where this theta 1 is basically sine theta. Now there are many unresolved sources in the sky. So what we basically observing are the superposition of such oscillations, which gives us this pattern like this. Now, as we see that, so for these 3 are for the May 6 data at different tapering, and we see that for the same night of data, as we increase the tapering, we see the foreground signatures are getting mitigated in 2 ways. So the overall amplitude is decreasing, as well as the amplitude of these oscillations are getting decreased. Now, considering f is equal to 0.6, if we increase the baseline density when we consider the combined nights data, we see that these foregrounds are getting mitigated even further, where we see that this decrease in overall amplitude as well as the amplitude in the oscillations, right? So this is also demonstrated in this figure, where we show the entire L and delta nu range for the multi-frequency angular power spectrum, and we see that for May 6, as we go from f is equal to 5 to 0.6, we see the foregrounds getting mitigated, and for f is equal to 0.6, when we see the combined nights data, we see this amplitude and these oscillatory patterns are getting decreased even further. So this is the cylindrical power spectrum, and we see the effect of tapering here as well. So as we go from May 6, f is equal to 5 to 2 to 0.6, we see that this foreground wedge is receding as we increase the tapering, and this 21 centimeter window is opening up. So this shows the expected horizon line, and we see this area is opening up. And for f is equal to 0.6 for the combined data, we get the best results, where we see even further improvement. So the reason why this is happening is, in our estimator, we incorporate the tapering through the convolution of the visibilities, right? So in presence of denser baseline and more uniform baseline distribution, we expect that convolution to be more effective, which is why when from at the same tapering, when we increase the baseline density, we see that the effect of tapering is increasing. So this show the power spectrum for f is equal to 5 and 0.6 for the combined nights data, where we have fixed 2k perpendicular values, and we have shown the power spectrum along the k parallel axis, and we see these values fall from 10 to the power 9 millikelvin square MPC cube to around 10 to the power 4 to 10 to the power 5 millikelvin square MPC cube at the highest k parallel values. And these shows 1 sigma noise, expected statistical fluctuations due to system noise for these 2 tapering parameters. And we see that in this higher k parallel values, the power spectrum basically oscillates between positive and negative values. So this shows the absolute values, but we see that the values are oscillating between positive and negative values within this 1 sigma statistical fluctuations. So from here we have selected this portion of the 21 centimeter window, which we considered to be relatively foreground free, and we have checked the statistics of the power spectrum modes that we are measuring, that we are getting from this region. So they show the histogram for the variable of x, which is the ratio of the power spectrum to the expected noise, expected statistical fluctuations due to the system noise, right? And we see that if these modes were completely dominated by system noise, what we would expect is that we would expect this to follow a Gaussian distribution with around 0 mu and some estimated sigma is equal to 1. But we see that we get a positive mean from this region, and also this positive tail, which indicates that the modes that we are selecting are systematic and foreground dominated still. And this power spectrum, this sigma greater than 1 is showing us that the error estimates that we are getting from the noise only simulations are not enough to describe the actual errors. So what we have done is we have carried forward this factor and multiplied with the values that we have obtained from the noise simulation to get the actual error bars for the spherical power spectrum. So what we have done is we have spherically beamed this K modes to get the spherical power spectrum, and the best value that we get is the 2 sigma upper limit that we get is 133.97 squared millikelvin squared at K is equal to 0.347, which we use this equation to calculate this omega H1 VH1 factor, which we get to be 0.23. So this is the best value that we got using foreground avoidance. And there was another study using the same data, but 8 megahertz bandwidth at Z is equal to 2.19 that Obhiruda's group performed. So they got the power spectrum to be like this, where they got the best value to be 61.49 square millikelvin squared at K is equal to 1 MPC inverse. So we see that here we are getting around 7 times the value of the other study, but we can go up to smaller K values using our estimator. So to summarize, we have applied the TGE estimator to estimate the mass and power spectrum of a heavily flagged. So 55% data was flagged in the data that in the results that we showed, using uGMRT observation at a redshift of 2.28. And our analysis demonstrated that the estimator can recover the input model power spectrum with high accuracy over the entire K range. We also demonstrated that the TGE is effective in tapering the sky response to suppress the contributions from the sources in the outer regions of the field of view. And in the power spectrum, we also did not see any artifacts due to the flagging that was present in the data. We showed that in presence of higher baseline density, the effect of tapering is better. And we found the 2 sigma upper limit on delta squared K to be 133.97 square at K is equal to 0.347, which translated to an upper limit of 0.23. And both these studies, the values that we got are still magnitudes higher than the values that we expect for omega H1 and VH1. So, thank you.
Thank you, Srijita. Questions? Okay, Suman.
So what was the reason for getting 7 times higher value of this omega?
That we do not know. We know where the differences in the estimators are, but it is very difficult to see exactly why that difference is coming. Okay. So what this study did was, so they took the visibility along the frequency, first Fourier transformed it and then correlated to get the power spectrum values. And to deal with the flagging, they used one-dimensional clean. And what we did was, we first correlated to get the multi-frequency angular power spectrum and then Fourier transformed it. But we see that for us, we are getting the input power spectrum back, right, from the simulation. So why this difference is coming, that it is very difficult to say.
Kanan?
I had the same question. Why do you see the difference? Do you also analyze? We have 5 nights of data. Do you see the same
4 nights and
4 nights of data?
combined data.
Yeah. So do you see same results for each night?
Yes, they are consistent.
They are consistent.
Yes.
Okay.
So I just wondering about why you have two large error bars at those K scales, because the other study CH21 that
So-
they also have similar K scale, but the error bar was smaller. Similar K value. I mean the
okay, you
middle.
are asking about these error bars.
Yes, the two error bars, the large.
These two. So
Yes.
we think that it's because the baseline density in particular these grid points were probably less, which is why we get this.
But for the first one, I mean
Yeah.
the other not that one, the first largest one. Yes. The other study also, I mean the CH21, they have similar kind of K value, but the error bar is smaller for the same.
So I don't know about this one. So they have, but for us, what we understand is that they used around 8 megahertz of bandwidth, right? But we are using 24.4 megahertz of bandwidth. So because of this, we see that where the baseline density is higher, we are seeing that the error bars are lower, right? However, we think that because the baseline density is not that much in these K points, that is why we are getting this bigger fluctuations.
Okay.
Any other? Okay, if not, let's thank Srijita again.